Hi, today I'll be presenting the Bayesian analysis of carbon emissions for Melbourne CBD buildings. This study was based on data from the Building Energy Efficiency Register, and the objective was to predict carbon emissions using energy consumption, building characteristics, and operational details. The dataset we used is from the year 2013, comprising carbon emissions data from neighbors' rated buildings. The dependent variable in this study is annual emissions, which represents carbon emissions in kilograms of carbon dioxide. The independent variables include annual consumption, rated area, net lettable space, FS level, and rated hours. Initially, the dataset contained 60 variables and 17,725 rows. We worked with a random sample of 5,000 rows and selected 5 features based on their correlations with the target variable to build our model. To better understand the relationship between these variables, we performed visual analysis. The correlation matrix indicated a strong positive correlation between annual consumption and annual emissions, while moderate correlations were found for rated area and net lettable space. Scatter plots also showed a clear linear relationship between energy consumption and emissions, while the relationship between FS level and rated hours with emissions were less defined. For the model specification, we used a Bayesian multiple linear regression model with 5 predictors. Priors were specified based on expert knowledge. Annual consumption had a very strong prior, rated area had a strong prior, and net lettable space had a moderate prior. Weaker priors, modeled as uniform distributions, were assigned to FS level and rated hours. The residuals follow a student t-distribution to account for potential outliers, and the data was standardized for better model performance. The model estimated parameters with high precision, as shown by means and 95% HDI ranges. For example, the coefficient of annual consumption was 0.234, indicating a strong positive association with emissions. FS level had a negative coefficient of negative 2867, while rated hours had a positive impact of 1441 on emissions. The model diagnostics indicated good convergence and performance. The trace plots showed stable mixing and with no significant trends, and autocorrelation dropped to a near zero after a few lags, confirming efficient mixing. The effective sample size was high for all parameters, and MCAC was low, ensuring precision in parameter estimates. The posterior predictive checks showed a strong overlap between the predicted and observed emissions, reflecting a well-fitting model. In conclusion, the Bayesian model successfully identified key predictors of carbon emissions, such as annual consumption and rated area, with a coefficient of determination of 0.959, meaning that 95.9% of variance in carbon emissions is explained by the model. However, some gaps remain between predicted and observed values in certain ranges. Moving forward, the focus will be on improving the model by refining it in areas where discrepancies exist and incorporating additional data and parameters in future models.